This is the last distribution in the chapter, and this is the infinite sheet of charge. And so the goal of this section is to determine the electric field for this charge distribution. And this XYZ and this red rectangle that I've drawn in here is an infinite in the XY plane sheet of charge, and so it's located at x equals 0, and it goes, infinitely up and infinitely over here and infinitely down. And we want to figure out what is the electric field, around this infinite sheet of charge. And we need to figure out which coordinates. So which components are present, just like we did before on the infinite line charge. And so we look at we're going to do this in rectangular coordinates. So that's x comma y comma z. And if we look at the x component, and how the book presents it is we take this infinite sheet of charge and we divide it up into an infinite number of line charges. Okay, and so here I've shown you this dy is just a section representing one piece of a line charge. And I guess I forgot to say it, but this would be characterized by rho s for a sheet charge in coulombs per meter squared. And so we have this infinite sheet charge that's broken up into an infinite number of line charges. And so if we pick a point out here along the x-axis, and we'll call this p comma x comma y comma z, and then we're going to pick a point here where this differential is at, and we'll call this the other point. It's going to be at x is equal to 0, and then some y, and z and z. Well, at this point, I should write it as, we're just writing it right on the axis. So this could be 0, comma, no, not 0. This is going to be x, because we just said it's at some point x. And so we'll just call it x, comma, 0, comma 0. I think that's better. And this will be just a point here. I think for simplicity, we'll just use it right here. So we'll just call this one oops, 0, y, and 0 for this. And so now this vector to the charge r prime is just going to be equal to x, no, y, ay. So r prime is equal to y, ay, and then r, which is going out here, is going to be equal to x, ax. So that makes it easy. And then the vector from the charge to the field point r is going to be r minus r prime, which is going to be xax minus yay. Okay, so we got everything kind of set up. And what I was saying back here is we want to see which component of the electric field is present. And if we vary x by Coulomb's law, if we just say this is a little differential charge right here, then definitely there's an x component. So yes, there's an x component. And then if we look at the y, if we move y anywhere, just like on the line charts, there's always a y over here and a y over here, and it's infinite. So each side's going to cancel it. So no by symmetry. And then z is going to be the same thing because it goes infinitely this way, infinitely this way. So no matter where I pick a z, there's always an infinite equal number of charge below it and above it. So again, no by symmetry. So we only have to work out what the x component of the electric field is, how I've set it up. And so, like I said, we're going to divide this into an infinite number of line charges. And the formula for the line charge, again, was rho L over 2 pi epsilon 0 rho A rho. And so we need to figure out, I'll change the color here, what we're going to put in for rho L, and what we're going to put in for rho, and what we're going to put in for A rho, the unit vector. So A rho is 3. So number 1, so rho L is just going to be our rho S times dy, because this because we divided it into an infinite number of little tiny lines of charge. And then we have R, and so the magnitude of R is just going to be equal to rho, which is going to be equal to the square root of, here's our rho right here. The magnitude of R is just going to be x squared plus minus y squared, which is equal to x squared plus y squared, square root. And then our unit vector is just going to be r over the magnitude of r. Now, r was all of this stuff, but since there's no y component by symmetry, we can just ignore it and just say that we're going to use in the formula, our A rho is going to be equal x a sub y over the square root of x, x squared plus y squared. So now we have all the pieces here. So we're going to say dE is going to be equal to rho L, so we would say rho S dy, and then we have 2 pi epsilon 0, and then we have to put in our xay over x squared plus y squared. I think that's everything. And then and so if we go back up to, so this was our rho L, and this is our A rho over rho, this whole term over here. I've just taken this x squared plus y squared, the square root of that, times each other to get that formula. So now if we want to figure out what E is, we're just going to have to integrate from negative infinity to infinity of rho S dy x ay over 2 pi epsilon 0 x squared plus y squared. And we could rewrite this as rho S is a constant, 2 pi epsilon 0 is a constant. Let's see what else. X, we're not integrating with respect to x, so we could pull that out. can leave that in, and we'll just say ay here. And then we have the integral from negative infinity to infinity of x dy over x squared plus y squared. All right, we're getting close here. And so to solve this, we just have to look up, and again in a table, what is the integral from negative infinity to infinity of x dy over x squared plus y squared. And if you plug that into your calculator or computer or look it up in a table, you find that this comes out to be equal to pi. And so now we can take our electric field and we go rho s over 2 pi epsilon 0 a y y. I made a mistake here somewhere. Oh, okay, I see what I did, where my mistake was. This should be ax, okay. And this should be ax. And this should be ax, which makes this ax. And then times pi, because that's what the integral came out to be. And so that equals rho s over 2 pi. Nope, we don't have any pi anymore. Those pi's cancel out. So the pi's cancel out. This pi cancels out with this pi. And then we have 2 pi epsilon 0 ax. So that is the electric field for a sheet charge in the xy plane. Now the book will rewrite this so it's more generic, and they will just call this the electric field is equal to rho s over 2 epsilon 0 a sub n, where this a sub n is defined as outward, so it's a unit vector outward normal to the surface of the infinite sheet of charge, of the infinite sheet of charge. And so if we had say 2 sheets here, so we're going to draw an xyz axis, x, y, z, and we'll have an infinite sheet of charge located on the at x equals 0, and then say we'll have another infinite sheet of charge located at, say, x equals a. And then you want to figure out what is the electric field, say, outside of it, here at this point. And so the electric field at, say, point, we'll call this P, okay, at P is going to be equal to the electric field from the first sheet, we'll call that 1, plus the electric sheet field from the second sheet, which is going to be equal to, oh, I didn't put any rho s's, so let's say this is equal to, we'll just give it some generic value. It has a charge density, a sheet charge of rho, and we'll call this one a minus rho. And so we'll have the first guy, which is going to be rho s over 2 epsilon 0, and the unit vector is outward normal, so it's going to be this way. And so that would be a positive ax. And then plus a minus rho s over 2 epsilon 0. And then what is its unit vector? Again, it's outward normal. So outward normal is always out of the surface. And so that would be a positive ax. And so if you add these two together, you get 0. And if you're studying EE, then you could just say, yeah, this is a model for a parallel plate capacitor. So this tells you that the electric field is 0 outside of a parallel plate capacitor. Now what would it be if we pick some point in here? Okay, so let's do the same calculation again. E is going to be E1 plus E2, okay? And so E1 is still going to be the same. This is outward normal to that point. And so we're going to have rho s over 2 epsilon 0 and a positive ax. And then we throw in our other stuff, minus rho s over 2 epsilon 0. But what is this one now? Now the vector is pointing this way to that point. And so this is going to be a minus ax. And so we end up with 2 rho s over 2 epsilon 0 ax. Okay? And these cancel out. And so this is rho s over epsilon 0 ax. So that tells you that the electric field inside of a parallel capacitor is going to be this. So outside it's 0, inside we have some field. And like I said, I've drawn along the x-axis, but you could have just done it like this. Okay. And so we could have had an infinite plate here along the z-axis and another infinite plate, say, down here. And this was, say, rho s, and this was minus rho s. So this is x, y, and z. And let's say this is at z equals 10 and z equals minus 10. So infinite plate parallel capacitor, and then we find the electric field, say right here. And so we just say electric is equal to E1, and we'll call this E1. This is plate 1, this is plate 2, and so E1 plus E2. And so we use our formula again, rho s over 2 epsilon 0, and now we need to figure out what is the direction. And so if you look here, and I said this outward normal, but I should just say that's probably not a good definition for this type of thing. It's just basically the direction of the vector to the from the sheet to the point. Okay, I think that's a better explanation. And so we have a vector pointing down here, and so that's going to be minus az, and then we're going to have the other guy, minus rho s over 2 epsilon 0, and then this direction here for this sheet is going to be minus az. And so again, if we had sum that up, that's 0. And you could put more sheets in there if you wanted to. And you just always just apply this formula right here. So you're always just going to, for any type of sheet charge, you're just going to apply this formula right here. And then plug in. So A sub n, like I said, I kind of said it wrong the first time. It should I think a better definition for these types of problems is just from the sheet to the field point. What is the direction of that vector?